Hello, good evening, good morning, good afternoon, everybody, wherever you might be. Today we welcome someone from Kraków, ARKADIUSZ BOCHNIAK. I understand you are a PhD student of Uniwersytet, right? Yes. And it is our pleasure to welcome you aboard and to have you speaking about quantum correlations on quantum spaces. The Zoom is yours. Take it away.
Okay, thank you. Yeah, so as it was said, I will try to describe some type of quantum correlations on quantum spaces. So let me first maybe say that this is the work done jointly with Paweł Kasprzak and Piotr Sołtan. And let me start with maybe explanation of the title. So some basic things. So let's start from the very beginning. So first, the quantum space, so the first part of the title. So the quantum space is an object of the category dual to the category of sister algebras, and as you probably well know, the standard notation is that we denote the quantum space by X and the corresponding sister algebra by C of X or C0 of X. I will use mostly C of X because in my talk I will use the unit arcanes. But from the very beginning, I start with this C0 just to have everything written. And okay, so the quantum space is said to be compact if the corresponding sister algebra is unital, and it's called finite if the sister algebra is finite dimensional. And other properties of the quantum space will be defined in terms of the corresponding sister algebra. So what I will talk about are the sister algebras, but I have the, let's say, picture that I am consider some kind of quantum spaces. But what we are we are working with sister algebras. Okay.
May I have a question?
Yes.
What morphisms between non-unital sister algebras you allow?
Okay, so the arrows will go into the multiply algebras.
Okay, thank you.
I should mention that for the C0 case, of course. And all the diagrams I will draw will be for that. So if I write C0 of X on the commutative diagram, it will mean that the arrow really goes into the multiply algebra. Okay, I think I should mention that. Okay,
and
so
also
that's
you assume your morphisms to be non-degenerate, yes? Non-degenerate maps.
I think, yeah, in this case, yes.
Okay.
Okay. Yeah, but I will briefly, I will in a minute start with a compact case, so it will be much easier. So I don't need all the subtleties here. Okay. So that's the first part of the title. So we know what is the quantum space. So let me go in for the discussion of the second part of the title, which is which are the quantum correlations. So let me start with some, let's say, classical motivations. So suppose for a minute that P and O are some finite sets, and the quantum correlation is for me any collection of non-negative numbers P with 4 indices A, B, X, Y, and A and B are elements of the set O, X and Y are elements of the set P, such that those two maps are probability distributions on the set P. And the notion, the definition is motivated by, or is originated from the information theory. So you can have some kind of non-local games. You have two players, Alice and Bob, and you have a set of questions and a set of answers, set of possible answers. So P will be the set of question or set of answer, and you have a game in which you give both Alice and Bob some elements from set P. So in this case, this is X and Y, and they give an answer A and B with some probability. So that's the, let's say, origin of this construction. But in general, I'm just considering some set of non-negative numbers such that those two maps give me probability distributions. but the origin is from the theory of non-local games. And I will make a lot of, let's say, connection to the non-local games in my slides. So this is just some kind of motivation.
Sorry, may I ask you a question? Could you come back? Yes. What is quantum in this picture? Because everything is probabilistic.
Okay, so the name follows from the situation when we have those two players, Ice and Bob, and you can assume that in certain situation they are sharing some entangled state. So you have some Hilbert space, and this is like a quantum mechanical situation. So you have a Hilbert space, you have two observers which are making the measurement, and you are assuming that they can share some entangled state. So
yes, I understand this, but here you do not have any amplitudes of probability. You have only probability distributions. So these are only functions. There are no Hilbert space.
Right. In this case, this is just a name, but the origin of the name is that in certain situations, those numbers can be computed out of the quantum data, which are just the quantum mechanical data. That is the explanation of the name. Okay, it's true that in this situation, this is only the name, but for some more specific choices of the, let's say, of the frame of the sets PAO and how the game looks like, we can have a description in terms of Hilbert spaces, and the players can share some quantum state, and then the name have some deeper meaning. But for this page, it's just a name.
Do you have Hilbert spaces in your talk or not?
In the next slide there will be Hilbert space.
Thank
you. In this slides that we have a Hilbert space. So I will discuss mostly one case of the correlation, which is the so-called quantum commuting correlation. So in this case, we have a Hilbert space H, and we have two families of projections in B of H, and the numbers P are constructed in that way. So we have this norm one vector in the Hilbert space. So we have a fixed norm one vector, two families of projections, and those numbers are constructed out of those data. So this is the one possible example of such quantum correlations. And we are assuming that those projections commute. So for any x, a, y, and b, we have this commutation rule that explain the part commuting in the definition. And we are also assuming that the sum of all projections E, X, A, the sum of A is identity in the same for the second one. So this is like to ensure that we are having the probability distributions in our case. So that's the one example, I would say classical example, but there is a name quantum here. But in some sense, there's a classical example because what is classical here are the sets P and O. And our goal is to somehow have some notion of quantum correlations, but in the case when the sets P and O are replaced by the quantum analogs. So you would like to have some language or some theory for quantum correlations on quantum spaces. So this is.
Can I ask another question?
Yes.
Do you allow states which are not pure?
On which level? I mean, here.
Yes,
right?
in this definition, you have a unit vector in Hilbert space, which means that you are computing the correlation between in the state which is pure.
Right. In this case, right. But in general, those are just some numbers which can be computed out of. For me, it's not important what is really the origin of those numbers. So what I would like to discuss is mostly this thing. So I have some numbers such that those two maps are probability distributions. And this is just an example how to get that number from some, let's say, more physical framework. So I have some Hilbert space and unit vector, then from the family of correlation of projection, I can get the set of such numbers. So there's other motivation than the, let's say, exact formulation of the problem. So I will try to describe the let's say, a rigorous formulation later on. This is just to motivate what, this is just to show what are the motivations for considering those objects. So in the classical case, we have some classical distributions. In quantum mechanics or quantum information, we have some probability distributions computed out of given Hilbert space and projections. And one possible example of such family of projections that they are commuted, but there are also different possible choices. So we can have, for example, correlations which are, then the maps, the numbers P, which are constructed out of the, not one Hilbert space, but we have two Hilbert spaces, one for the, let's say, player Alice, the other for Bob. We take the tensor product and we consider the operator on this tensor product. So there's out of possible choices, this is just one example. So this is only to motivate the, let's say, the work. It's not like to have a precise definition at this level, okay? Does it answer the question? Or?
My question was very simple. Does purity of this state play a role or not?
Of course, it will play a role for some properties, which I will discuss later on, but from the very construction, we don't need it. So,
okay, thank you.
Okay, so as I said, we would like to have some generalization of those notions for quantum sets. And this is inspired by previous work by Bernard and all, where they constructed or they discussed the non-local, the games where this is the quantum to classical games. So one of the sets was quantum, the other was classical. So this is like the partial quantum situation, right? So only one of the sets was quantum, but we would like to have two of them quantum. And also we would like to have the quantum spaces not to be only the full matrix algebras, but we would like to have slightly more general situation. So, okay, so this is just to say what is the goal and what is the motivation for this work. And as I said, some of the tools, some of the techniques were motivated by those two papers. And also we were able to, in some cases, find some more deeper origin of some properties which holds for specific sister algebras which will appear in this construction. So this is just to, let's say, make some brief summary what will happen now. So let me start to discuss the first paper I mentioned. So in this paper, the crucial object was some universal sister algebra, which was associated to the game they consider. So as I said, this is the quantum to classical game. So there was some quantum space. So in this case, the corresponding sister algebra was just a matrix algebra of dimension n. So that's the reason of this number n here. And the other space was just C to power C, so C copies of complex numbers. So that's the origin of this second index. So they had this sister algebra, and it turned out that a lot of properties of the game can be deduced by just looking at this and just examining the properties of the sister algebra. So this is somehow
sorry, I just have a stupid question. What's the difference between PIs and PNIs? Because you have PNC and you have P1 to PC. What's the difference with two index things and?
This.
Yeah, because this is the algebra. I'm so sorry. Yes.
Yeah.
Okay. Yeah. Yes. Okay. I'm so sorry. Yes. So these are okay, and so that's generated by entries of the orthogonal projections that add up to 1. Okay. So, but this is then this PNC. It's just a commutative sister algebra, right?
Why?
What is the sister algebra? It's generated by C orthogonal projections.
Right.
So to me,
entries of the projections.
Entries of the projections. Okay.
Right. So I have some small p with index C and let's say index k and ij. K is from 1 to C and ij from 1 to n.
But what is an entry of a projection? I understand it's a projection on some Hilbert space, right?
Oh, it's in matrix algebra, I think, but still I don't understand this definition.
I don't understand this definition, sorry.
Wait, I have a question.
Yeah.
Mm-hmm.
Go ahead, Paul.
Oh, going back to the very beginning of the talk, can you show, so you have two finite sets, and then there are projections in a Hilbert space, and there's a lot of commutativity. Can you show us an interesting example of this? Of what can you produce for us an interesting example of this situation?
Okay, I don't have the example right now.
I mean, what are we really talking about here? I mean, when do two projections on a Hilbert space
commute?
When do they commute? I mean, one is.
I mean, we can take, for example, the Hilbert space, which is the tensor product of two Hilbert spaces.
Mm-hmm.
And one of the elements is like having something on the first leg and the other having only something on the second leg. That's the most trivial example.
Yeah,
yes.
Mm-hmm.
I see. And you would use something like this to produce interesting examples? That's how this works?
I mean, the whole story about the graph homomorphism games is about examining some such kind of objects. So
the whole story about what? About
there is a quantum homomorphism game. So it's a way to determine if there is a homomorphism between graphs. We have a given graphs, and the question is, so suppose we have two players, Alice and Bob, and we are giving them, we are asking them by giving them two vertices, and if okay, let me just go back to this. Okay, so the goal of the game is to check if two graphs are isomorphic. Okay, and there is so each round is as follows. So we are asking the players if okay, we are giving two vertices to the one player and two vertices to the other player, and there is some function which is called a verifying function, and if the function of those four numbers is equal to 1, then we are saying that the game is win, so that we found the isomorphism between the two graphs, and if not, then those graphs are not isomorphic. So this is the framework to determine if there exists isomorphism between two objects. So, I mean, this is one of the applications where this was used. I mean, I don't have some very down-to-earth application right now. paragraph.
But the construction of this whole package of projection is not so straightforward. Yes, it's somehow convoluted. It's not explicit. Yes, in this game.
Right, yeah, it's not so explicit in general. So yeah.
But this set of projections is something which is called quantum strategy. Yes.
Yes, this is another name.
Okay, let's go on. So can we come back to my question? Well, I understand that you have the tensor product of the sister algebra P and C with n by n matrices. That's perfectly okay. But now I try to understand the sister algebra. So I have C orthogonal projections. C and n are unrelated, I understand. These projections are orthogonal and they add up to 1, to identity on the Hilbert space. Fine.
Yes.
But I don't understand what is an entry of a projection. I mean, projections operate on a Hilbert space. What does it mean to say that I have an entry of an operator on a Hilbert space? I don't understand it.
Okay, so you have we have a matrix, right? With a n by n matrix with
but I want n equal to 1. I want n equal to 1. Then what are we talking about? What is P1C? Let's take n equal to 1. No matrices.
I mean, it's a trivial situation because then we have just. I mean, this is like. Yeah, this is a trivial. So the first non-trivial is n equal to 2, right? We have to have at least. If I have a matrix 2 by 2, I have four entries of the matrix. Right. So, and then I'm taking matrices, 2 by 2 matrices, which are projections. So there will be, so suppose I have, I don't know, P1 up to PC matrices, PC projections. Each of them is a 2 by 2 matrix. And I can take the entries of this matrix.
These are
They are projections in this algebra, not in the PNC.
So maybe the other way to put it is like this. Imagine that n is equal to 2. Yes, you have, and C, for example, is, I don't know, 3, for example. And then you have 3 projections, each of them, each of which is a 2 by 2 matrix. So you have 12 altogether elements, and this sister algebra is generated by those 12 elements and subject to some relations. And those relations, all possible relations, are only those relations which follows from the fact that these matrices are projections and that this projection add up to 1. Am I right? Is it?
So Adam, so if what you are saying makes sense to me. But then this should be this P1 to PC are elements of a matrix algebra because this is a vicious circle.
Yes, and they are.
They are.
Yes, they are.
But it says matrices over P and C. So for me, this is a vicious circle. You define the sister algebra by saying that it generates by elements of matrix of a sister algebra, which you just defined.
It is written as it is. A
wrong
vicious
definition.
But as I understood it, is.
I can explain it. I can explain it. So what are these projections in matrix algebra with some entries? Let's call the algebra of entries B. So this is the algebra map from C to the power small c. By C, by this capital C, I mean complex numbers, to the algebra of matrices, n by n matrices with entries in B. Okay? And universal construction in this context is finding such an algebra that such homomorphisms are the same as algebra maps from some algebra P and C to B, to the algebra B. Okay, so this is a universal property. And this algebra P and C is a solution to this universal property. In other words, you can speak about the functor, which applies to an algebra B can produce matrices, n by n matrices with entries in the algebra B. Then you can construct the left adjoint to this functor. And if you evaluate this left adjoint functor on the algebra of c to the power small c, you obtain this algebra P and C.
I'm sorry, you have to write it down. If
Well,
sorry, I don't understand it.
May I?
Yeah, go ahead, Bartek.
So I really cannot see anything wrong with this definition because there is no, not really a vicious circle here, because simply what I mean, you would, if you were declaring like an ordinary sister algebra by a universal construction, you would just say that the sister algebra A is the sister algebra generated by elements A, B, C, D in A, which satisfy those conditions by some universal construction. So here is precisely the same. Simply this P1 to PC stands really for the whole matrix of elements in the algebra, which you are just
okay, Bartek, it makes sense.
This.
Yeah, thank you. I understood it. Yes, thank you.
If I just may add something.
Thank you, Bartek. Yeah, go ahead.
Yeah, so I think the construction possibly might be similar to what was the construction by Alain Kohn and Michel Dubois-Viollet. I mean, that was not for actually using the projections, but using unitaries. And that was the construction of these non-commutative three spheres. And that was basically the same sort of idea, defining the algebra through the relation implemented in unitaries. So maybe this is just the same thing or similar thing.
Yeah. I understood it when Bartek explained. Sorry for the interruption, but I was really
Can you see my
confused by
writing?
the way it's written down.
Can you see my writing?
Yes.
Yes.
Okay, so this datum, the choice of C orthogonal projections summing up to 1 is the same as the algebra map from C to the power C to matrices n by n matrices of with entries in B.
And what is B?
Any algebra. I'm explaining the universal property. So what is this PNC? This PNC is such an algebra that such a datum above this horizontal line is equivalent to the algebra map from P and C to B. Okay? And this can be described, so this is the definition. This is the right definition. What is PNC? Okay? This functor of matrices, n by n matrices, has a left adjoint. Okay, and left adjoint applied to this C of C, this is by definition PNC. And then if you have such a map, then you have the counit of this adjunction. Counit or unit of this adjunction. Okay, so this means that you have a map from P. P. Let me erase this. Okay, so since L is a left adjoint, then you have matrices.
Well, maybe it's taking too long, Tomek. I understood, and
I doubt.
maybe not
I doubt
interrupt
it
for so long.
I doubt it. I doubt it because what was explained was not explaining neither the universal property of this construction, and this universal property is a definition of this object, and the relation between these projections regarded as matrices with entries in this universal algebra. None of these things were explained. So it's hard to say that anybody could understand what was going on. So the point is that there's a transformation from identity to matrices with entry in this L. If you apply this to C, to the power C, you obtain a homomorphism P and C. And this is precisely the choice of P1, PC in matrices with entries in P and C. It's a unit of the adjunction which I wrote below. And this is the right definition, mathematical definition.
Sorry, am I right by saying that these projections in matrix algebras are in fact somehow artificial? They're only for convenience, only for writing those all possible relations in some more compact form.
Well, that's precisely what I said. The statement.
Exactly. So okay, the other way would be just to write all possible relations, which follows from the fact that capital P J is projections, and all these projections sum up to one. But this would be tedious. But this is some list of relations, and in principle, one can write all these relations. And then you take universal sister algebra with n squared times C generators subject to all those relations. And universal means this property of extending morphism, yes?
Right. Yeah, it was meant by this. So we just have a
okay, thank you.
Entries as elements which generate, I mean, we take the entries at the generator of some universal sister algebra subject to some relations, and the relations are encoded in those conditions, roughly speaking.
Mm-hmm.
Sorry, but can I ask maybe an even stupider question, but in a very naive, maybe I'm completely wrong, but if you have a set of orthogonal projections with some one, what they generated in universal sister algebra is C to the power number of projections. Yes. So this is just n times n matrices, tensor product with C to the power number of projections, the final algebra.
No, it's not so. This left adjoint is much more complicated. It's generated freely by these entries of matrices subject to some relations.
Okay, yes, so sorry, yes. Yeah, sorry, I was completely wrong. I thought that the entries of these matrices were orthogonal projections. So it's the complete opposite, sorry. Thanks.
Mm-hmm.
But it was confusing. It was confusing. So apologies for such a long disruption, but this was confusing simply, and we wanted to figure it out. Okay, go ahead, Ark. Go.
Okay, so now let me. Can we erase this?
Tomek, erase it.
I'm erasing this.
You can erase it in one click.
How? Where is erase?
Clear
everything?
all drawings.
Clear. I cannot see such a button.
But you have it.
Clear.
Okay.
No, it doesn't work. It would be.
Yeah, it works.
It works.
Okay. You can do.
Okay. So now let me go a little bit further. So we had this sister algebra described by those projections, and then we can observe that the set of projections P1 up to PC define a star homomorphism given here, and we can say that this homomorphism is universal in the following sense, that if you have any other map from the set on the left-hand side to this tensor product, then there exists a unique star homomorphism lambda such that the appropriate diagram commutes. So this is the property which we would like to mimic on the purely quantum level. So that's the, let's say, starting point of the construction of, say, the family of quantum family of maps between quantum sets. So I will do this now. So let me first remind some definition. So suppose we have 3 quantum spaces, and then we can consider something which is known as the quantum family of maps from a set P to set O indexed by a quantum set X. And this is just a morphism from C0O into the tensor product C0P tensor C0X. And here the tensor product is the minimal one. Later on, I will use different tensor products, but for now, I mean, in this part, it's just the minimal tensor product. And having this family, we are ready to consider the main object we will discuss here. So this is the quantum family of all maps from P to O. So it is defined by mimicking the previous property. So mainly we have the following commutative diagram. So we say that phi PO is this quantum family of all maps if for any quantum family psi going to the C0P tensor C0X, there exists a morphism from C0, and this is the universal space we would like to have in this corner. So this is the set which we'll call the quantum space of all maps. So there exists this morphism lambda such that this diagram commutes. So this is the definition of the both the quantum family of all maps and the quantum space MPO of all maps. So this defines the per phi and MPO. So okay, so the first observation, which follows directly from the universal property, is that if this pair exists, then it's unique up to isomorphism. And now there's a question when it exists. So, for example, it is known that if P is finite quantum space and O is the compact quantum space, then this object really exists, and moreover is a compact. I mean, this MPO is a compact quantum space, and we can describe the corresponding C-star algebra as generated by this set of elements. This was.
May I have a question?
Yes.
So the idea is that it should somehow mimic in the non-commutative setting the space of all maps from P to O, yes, in the quantum sense. And even in classical case, okay, you can speak about the space of all possible continuous maps from P to O, but this would be too huge to be locally compact, yes, in general. So this is the problem, that in general, you don't have any chance for this thing to exist, yes?
Right, exactly. Okay. But in this quantum setting, it exists, and moreover is compact.
So classically, it exists, but it is not locally compact. Therefore, yes, it cannot be translated into C-star algebraic language. Yes.
Arek, one question. I mean, the classical counter example, not counter example. Classical example would be a finite space. So
Right.
just dropping the quantum. So it would be the maps from a finite space.
Right. So for finite it's fine. The problem is if we are beyond this finiteness. So the simplest example are some maps on circle or something like that. So then you have some you may have some problems. That's some. I mean,
Okay.
But the finite is important.
Finite is important in the quantum case, but I mean, the classical counterpart would be finite points or just points, set of points, finite set or?
Yes, finite set.
Finite set, okay. So then probably what Adam said, I mean, is...
if for finite is fine, yeah, but the problem is if P is not finite. That's the main.
Okay, but if P is finite, then everything is okay.
Yes, for both classical and quantum, and mostly for the quantum case, the finiteness is important. And later on, there will be another important property of the second algebra, I mean the second set, that the algebra CO is separable. But at this level, we don't need this, but in the next, for the next properties, we'll need the assumption that CO is separable. So this is just two.
Can I have one more question about this?
Yes.
Could you explain, for example, in the classical setting, does this space will exist if both spaces are compact? Or already here the problem appears?
Classically, it would exist, but it would be not, the space of all maps would not be locally compact. Therefore, one cannot speak about the sister algebras of all.
By existence, I mean being locally compact. So already from compact to compact, it is not locally compact, yes?
Yes, in general, it wouldn't be.
Okay, thank you.
Okay, and okay, so just a remark that this sister algebra PNC is exactly the algebra CMPO with CP being the matrix algebra, the full matrix algebra, and CO being just C copies of C, so as it should be. Okay, so that's the object we have, and now we can go and try to check if the properties of PNC, which were crucial in the case of this paper, are also holds in the purely quantum case. So first we start with the residual finite dimensionality, so the RDF property. So we are saying that sister algebra is RDF if it possesses a separating family of finite dimensional representations. And this property is important because then we can have traces, and traces are crucial for the applications in quantum information. So being motivated by the possible applications to quantum information, we would like to have the sister algebra which has the traces, and let's say, maybe not the simplest, but one of the possible ways to have a RDF sister algebra. So we would like to know if our sister algebra is RDF and when it is RDF. So the simplest example of RDF algebra is this first sister algebra of a free group of two elements. It was proven by Choi in 80 that this algebra is RDF. And in the paper by Brana et al., the algebra was also RDF. So as I said, it would be nice to know if our sister algebra CMPO is also RDF. And to do that, we need to describe the disjoint sums of disjoint unions of quantum spaces. So first, let me just define the disjoint union of quantum spaces as a quantum space such that its corresponding sister algebra is the direct sum of the sister algebras. And from now on, I'm assuming that both P1 and P2 are compact. So I am using C instead of C0 in each place. So only the compact case is now important for me. And okay, so we have this notion of disjoint union. Then we can ask what is the sister algebra C MPO with P being the disjoint union. And this is simply the free product of those sister algebras corresponding to the spaces P1 and P2. So this is one of the results we have. And now this is useful in order to describe CMPO in general. And to do that, we need the following lemma. So suppose we have a unital sister algebra C and unital sister homomorphism from the full matrix algebra into C. And then we define the set D as the relative commutant of the image of the matrix algebra in the sister algebra C. And then it's relatively easy to check that this is a unital sister algebra and C is isomorphic to the tensor product of the matrix algebra with this set, with this algebra D. Okay. And this was used, this property, to prove the following proposition, which allows us to describe the set, the algebra CMPO in general. So this is like, okay, so the framework is the following. We have a compact quantum space O and a finite quantum space P. And we take the composition of the space CP into the matrix algebra. So we fix all the indices now. So M is fixed from now on. And then we can show that the sister algebra CMPO is the free product of D1 up to Dm, where Di is the relative commutant of this matrix algebra in this plot. Okay, and this is the first ingredient we need to prove that our algebra is RDF. Why? Because we have the following theorem. So if O is a compact quantum space such that CO is RDF and P is any finite quantum space, then CMPO is also RDF. And as I said, one of the ingredients is to know what is the description of CMPO in terms of a free product. And the other is the theorem by Axel Rowling that RDF passes to free products and to subalgebras. And combining those two results, we can relatively easily show that the theorem holds, so that our sister algebra is RDF. And as I said, it follows from this theorem that then CMPO has a faithful trace. And this will be useful to characterize further the quantum correlations. But this is now at this level just some property of the sister algebra CMPO. Okay, so this is the first property, and the other properties will be related to the more, let's say, functorial point of view on the space MPO. So to do that, we consider two categories. So the one is the full subcategory of the category of quantum spaces consisting of finite quantum spaces, and the other consists of compact quantum spaces. And then we consider the following mapping. So the pair PO, we associate the compact quantum space MPO. And it turns out that this mapping is a bifactor, and it remains to see how it works on the level of morphisms. So we take let's take two finite quantum spaces P1, P2, then two compacts O1, O2, and two maps ρ and pi, and then we define the associated map M rho pi as this lambda, which makes this diagram commuted. So this is the, let's say, construction of this construction. We know that this map exists. Okay, so it's not the construction, but this is the map we wanted. And now this functor can be shown to be, we can show that this this functor is contravariant with respect to the first variable and covariant with respect to the second one. And moreover, if we assume that now, for example, P1 is fixed, so P1 is equal to P2, and we are changing only O1 into O2 and considering a map which goes from O1 and O2. In other words, we are taking identity as a map row. Then we can, for example, show that if the map pi is surjective, then the corresponding map M identity pi is also surjective. And we have here the all properties of the functor. So we know that if pi is surjective, then M identity pi is surjective. If pi is injective, then M identity pi is injective, and so on. So most of the properties are relatively easy to prove. The second one was the most complicated, I mean the most technical one, but it also holds. So we have those simple properties. We can also ask what happened about the opposite algebra, and there's nothing surprising here that if CO is isomorphic to CO opposite, then the opposite to CMPO is also isomorphic to CMPO. And it follows from the proposition that if P is a finite quantum space and O is a compact, then this pair is naturally isomorphic to this. So this is one of the further properties we have. And just one remark that the assumption here is satisfied for O being a finite quantum space. So when we will later on discuss both P and O finite, then we will know that this holds and we can use it many times. So this is something we will use without, let's say, referring to it directly. But if we will know that O is finite, then it's fine. We can use it without any problem. I mean, both O and P, not only O. Okay, and this is the, let's say, first part related to the algebra CMPO. And now we are going to define some operator system which sits in this algebra, which is embedded in this algebra. And we will examine the properties of this system. So before doing that, we need some basic notion, basic definition. So let me just make some quick reminder of some basic notions we will need. So we will need the notion of the completeness. So we would like to know what does it mean that some map is completely positive, completely bounded, completely isomorphic, and completely everything. So you can just put any adjective you want. And so suppose we have two sister algebras A and B and a map between them. Let's call it phi. And then we can also consider the map phi n, which is just defined like here by this prescription. And we say that phi is a CP if phi n is positive for nn, phi is completely bounded, phi n is bounded for nn, and so on. And of course, if the algebras are unital, we can say about UCP maps and so on. So that will be the notion we will use from now on. Just in almost every propositional lemma it will appear. So it's good to have it written at least once. And we will use also the property of this of the UCP maps, which says how the UCP map behaves under the tensor product with compact operators. And this is the following fact, which we will use, that if you have a UCP map psi from A to B, then it defines a non-degenerate CP map from k-tensor A into k-tensor B, where k is just they're just the compact operators of L2. And this map extends uniquely to a UCP map between the corresponding multiply algebras. So we will use this fact very often. Moreover, we will use in some.
Sorry, by a map phi, you mean simply a linear map?
Yes, linear, of course. Everything is linear. Right. Okay. And then we will use also very often the notion of multiplicative domain and the property that this set is really a C-star subalgebra of this algebra A we start with, and the restriction of a map, of a UCP map from A to B to this set is a star homomorphic. So we'll use in some proofs though this fact. So I'm just making some summary of things which will be useful later on. And the basic property for which we will use this fact is to prove that if we have a UCP map between unital sister algebras and some element A from the multiply algebra of k-tensor A, then and suppose that this element belongs to this multiplicative domain C identity tensor phi, then for any functional omega on K, this element belongs to the multiplicative domain of C phi. So this is the fact which we will be using, which we will use many times to prove some of our results. So this is just to make some, let's say, maybe not dictionary, but make some collection of results from which we will deduce our results. And the last ingredient, which will be crucial to examine the further properties of the algebra CMPO and the operator system, which I will define in a minute, is one of the consequences of the Kasparov variation theorem. So we will use this consequence exactly in this form as written here. So we are assuming that we have a finite quantum space P and a compact space O with CO being separable. And the separability here is important because it is necessary to use the Kasparov theorem. And okay, and we also are assuming that we have a separable unital sister algebra B and the UCP map from CO into the tensor product of CP and B. And then from the Kasparov theorem, we deduce that there exists a map psi from the morphism of the star homomorphism C0 into tensor product CPKB, such that this map psi is something which you can call the first entry of the map capital psi. And here this omega 11 is just the this object. This omega 1 is just this map here. So E1 is the first vector of the standard basis of L2 in the canonical ordering. So this is the one of the crucial facts which we will use in the next few slides. So okay, this is the, let's say, summary of the tools which will be useful for us. So now let me go and define the operator system we would like to discuss. So first, let's see how this operator system was defined in the case of Bannon. So again, it is defined as a universal operator system generated by matrix elements Q, such that if you build the matrices QA from those elements, they are positive and they sum up to 1. And the notation is as before. So C is this exponent from C to the power C, N is from the matrix algebra N by N matrices. Okay. And
sorry, could you explain what does it mean to be a universal operator system?
Okay, so
I know the definition of the universal sister algebra subject to some relation, but what does it mean to be a universal operator system?
Okay, so operator system is a so linear subset of okay, so there are two ways of defining the operator systems. So one of them is by taking some subset of operators, right, on a given Hilbert space, for example, and you are assuming that this subset contains identity and is invariant under taking the involution. So the system S has the property that S star is equal to S. Okay, so this is any such set, and you can define this system as a universal operator system just by saying that. Okay, maybe I will show this in a minute because I have this example written. It will be easier to see on the example.
Okay.
Okay, so let me just first say that the universality, okay, can be expressed in the same way as for P, but to be more concrete, we had this those projections PA, and they enters PAIJ, right? They are the entries of the projections PA. So now this operator system will be just the linear span of those things without taking multiplication into account. Okay, so that will be the difference. So we are not multiplying. We are not assuming that the set is invariant under this multiplication. Does it answer the at least?
Still, I have some doubts, since if you are constructing the universal sister algebra, then this algebra is in fact abstract. It is general. Okay, there are some abstract theorems how to realize it as a subset of B of H, but concerning operator systems, you started with definition which already requires that this operator system is realized as a subset of B of H. So here I'm confused, since if you take some collection of projections, there could be some relations between them in concrete Hilbert space. So I'm confused.
You're right. Okay. So later on, I will show the other possible definition of the operator system, and then there's a theorem by Choi. I don't remember the date. I think it's 80s. That the abstract operator system is the same as the, let's say, concrete one. So in the sense, you can talk about universal systems just by looking at them from the perspective of operators from B of H. And then you can also describe them in a purely, say, abstract way, but you will get the same answers in some sense. So this is, in some sense, there's nothing wrong to have this picture in mind, that this is like having the operators on B of H. But you're right that there is another way of looking at the operator systems, but they lead to the same conclusions. You can have this picture in mind that if you have a sister, I mean the sister algebra which we had here, the universal one, then in some sense you can just forget about the multiplication and you will have the operator system, and this will be fine. So
correct me if I'm wrong. So okay, we start with this abstract definition, and okay, I agree that there is some there is a way to define what is an operator system abstractly, and then universality means that if you have another operator system with some bunch of elements, index the same amount of elements which generate this universal one, then you have what? You have not a morphism of algebra, since you don't have an algebra, but you have CP map, yes?
You have in our case, UCP map. Yes, exactly.
UCP map. I see.
Yeah, so you will have exactly the same diagram. I have it in the next slide with the morphisms, with the style homomorphism replaced by UCP map. So I showed before the commutative diagram for the CMPO algebra. So for the operator system, I will have an analogous commutative diagram, but with a CP map instead of the style homomorphism. That would be the difference.
And also you allow possible relations which are allowed are those which use addition, multiplication by scalars, of course, and involution. Yes.
Yes.
You are not allowed to use relations which involve multiplication of elements, since you don't have an algebra, but you still can use the adjoint operation. Yes.
Yes, exactly.
Okay. So now I'm fine with this definition. Thank you.
Okay. Having said that, we can now look at the at the situation we are interested in. So we have those two quantum spaces. One of them finite, so P is finite, and O is compact. And we can define the following operator system. And why this is so? Because we know from one of the previous theorems that those elements generate the algebra CMPO as a sister algebra. So we can now just take the linear span of those elements and take we just take the closure because it's infinite dimensional case in general. So and just to have everything well defined. And you can see that this is really an operator system, and the corresponding map is the same as before, but now we are looking at this map as going into SPO instead of CMPO. And we know that this set generates CMPO as a sister algebra, so just we can think of this map as going into SPO on the second, because the image is there. Okay, so we have this map, and then this map will be a UCP map. This is the, let's say, the dilemma we have, and now we can formulate this, it's a universality in this framework. So the universality is the following. So this map and the operator system has the property that if we have any other map psi, which goes to CP tensor S, where S is now an operator system, then there exists the UCP map lambda here, such that this diagram commutes. Okay, so this is the universality in our case, and this is something which really holds for the. I still have at times like I just sketch the proof. So the proof is relatively simple but technical. We are using most of the properties we discussed so far. So first, okay, we define the sister algebra generated by the elements we wanted to have as operator systems. And then we see that this is a unitary separable sister algebra, and the map psi is a UCP map. Then since we are assuming that O is such that CO is separable, we are using Kasparov theorem to get the morphism psi. Now having the morphism psi, we are on the level of sister algebra, so we can use the corresponding universality for sister algebras to get some morphism lambda from CMPO to K tensor B. And we are now going back in some sense. So we define a map lambda tilde, which is just taking this lambda and composed with omega 1,1 as identity, where this omega is as before. So this is the map which just gives me the, let's say, first entry. And then we just restrict this map to SPO and see that this restriction satisfy this required condition. Now we just make some finite slicing by composing with the functional on the first leg, and just to, and having that, we can relatively easily check that all the properties of generating the sets and so on. So everything is fine as it should be. This is like the sketch of the proof. So, and you see that there are two crucial parts. So first, the separability of the algebra to be able to use the Kasparov theorem. This is the crucial step. And then the other one is the universality of the algebra CMPO itself. So having those two things, we can say a lot about the algebra. We can show that SPO is a universal operator system, but it turns out that those two properties, I mean, the possibility of use the Kasparov theorem and the fact that we know a lot about this sister algebra allow us to deduce many other things about the operator system. So this will be done in a minute. So the first property we wanted to discuss, I mean, the next property we wanted to discuss of this operator system is the question how to say it, how good the embedding of SPO into CMPO is. Okay, so the question is, we know that SPO sits inside CMPO, but the question is how rigid it is. And to answer this question, we need to use the following definition. So the sister envelope defined by Hamana is a sister envelope for operator system, is a sister algebra, which is generated by this operator system. And the operator system is essential in this algebra, meaning that the complete order embeddings from to any operator system T are detected by restriction to S. So this is the notion of a sister envelope, which is, I think, well known, but it's just to remind it. And what was shown by Brannan and all in the paper is that the algebra PANC is the sister envelope of the operator system QNC. So the natural question is if we have the same property here. It turns out that, of course, it's not surprising that we'll have this property because I am just going in that direction now. But let me just mention that you can try to prove this, the case of Brannan, by some very technical, I mean, doing some very technical computation, very technical things, but there's something which may help us. And so when we were trying to prove that this theorem in our case, for our sister algebra, we were not able to really mimic those properties because they were really, in some sense, dedicated to those algebras, those specific constructions. So we were stuck at some point, and the solution was, and after all, very simple, but it took some time to realize what's going on. And the main thing which is important here is the fact that this embedding is hyperrigid. And the hyperrigid means that if I have two maps from sister algebra into B of H with some Hilbert space H, then if one is a star homomorphism, the other is a UCP map, and they agree on the operator system, they have to agree on the whole sister algebra. So this is the definition of hyperrigidity. And it turns out that having this property and the fact that the sister algebra—
May I ask a question?
Yes.
So what is the difference between hyperrigid and rigid? Like rigid extensions and hyperrigid extensions?
I'm not sure if I remember the rigid extension. I mean, there's always a question what kind of maps we have here. So in some cases, they are both star homomorphisms, in some, I mean, linear, in some UCP, 2 UCP. So I'm not sure what is in this, the other definition. In this case, we have 2 different types of maps. That's the crucial thing. So one is the star homomorphism, the other is the UCP. That's the crucial distinction between them. Okay. So this is the notion of hyperrigidity. And it turns out that if the embedding is hyperrigid and the algebra is generated by the set S in the usual C-star algebraic sense, then the C-star envelope of S is exactly this algebra. And this can be proven relatively easy using some very, let's say, not so sophisticated methods, but it turns out that you do not assume the second part. So you can just skip the fact that C-star of S is A. And without that assumption, you can show the same thing. And this was done by the paper of Harris and Kim in 2019. And of course, here A should be equal to A. I missed this information, but we just were able to prove this version, not using, let's say, other machinery, but some basic facts and some universal property analysis. So that was just to, just to show that this is like something which can be done simply using the universality in sense. Okay. Okay, so that's the.
Could you somehow elaborate, please, the difference between these 2 C-star algebras? I mean, C-star of S and C-star enveloping of S.
Okay.
Because if the main point of the theorem is that they are equal, because in fact, this is what immediately follows. So what it is here that coincides, which normally doesn't coincide?
Right. Let me think. Yeah, I was thinking about some simplest example of not hyper.
Maybe I can shortly explain.
Yeah, thank you.
So you have an extension, like you have your operator system sitting in some C-star algebra A, but you don't know if it's universal as a minimal extension, whatever this means. So you just say, for example, you have an operator system that sits inside A, and say as an and the C-star algebra generates inside A.
Yes. Okay.
If this is like already the minimal such extension. So extension means like you have like an operator system sitting inside a C-star algebra which generates it as a C-star algebra. But it's not clear if it's like a minimal one. You know, like you have like your maximal ones and minimal ones. Like you could have 2 different embeddings. Like you have one operator system, and you could embed it into one C-star algebra and into another one. And even though like you just consider the C-star algebra they generate in both copies, even though they are both just the C-star algebra generated, they may be still drastically different. That's like some peculiarity about operator systems. And so you could have some larger C-star algebra, you could have some quotient maps that go from one copy to another copy, but not the other way around.
So if I understand you correctly, the left-hand side, the C-star brackets S, that's just very simple. You just you are within already the C-star algebra A, and you see what is the subalgebra that you get by by using elements of your operator system. And on the right-hand side is like you want to have the universal enveloping C-star algebra of an operator system.
Yes.
Exactly.
And what you are saying is that in general, it might be larger, right?
Yes.
In the sense that there must be a quotient map from the C-star N of S into C-star S.
The other way around. So the smallest quotient is the C-star envelope.
Really?
Like the maximal one is the C-star algebra, you just call it the maximal C-star algebra generated by your operator system, and the smallest quotient, so the other end of the spectrum, you obtain the C-star envelope.
So it's like the opposite of when you consider, you know, reduced and universal C-star algebras, convolution C-star algebras of the group.
Yes, exactly. So there is a maximal C-star algebra generated by an operator system. That's usually just noted C-star without the n. It's like the maximal one. It will be corresponding to the full group algebra, say, and then you have the minimal one, like the complete other side of the spectrum, like the smallest quotient, to which S embeds into.
I'm puzzled.
You need to be able to always embed S. Yes, that was like a Hamana's like a big result like that. There is a minimal one. It's not just zero, because you still need to embed your operator system, and your operator system is of course non-trivial. So and you need to embed it, so the envelope can't be zero, right? It at least contains a faithful copy of your operator system.
Mm-hmm. So you say it goes exactly the opposite direction than with groups.
Yes, and the point is that in the maximal C-star envelope, you have the fewest relations. And the further you go down the quotient, the more relations you obtain, like the more nice relations you obtain. So the nicer your
Okay, I see it. Yes. But isn't it confusing to call it envelope? Yeah. Thank you so much, Alex. Yeah, this was very non-trivial. Yeah, I understand that you can try to squeeze the operator system into many smaller C-star algebras where it will still be embedded faithfully, but the C-star algebras have more and more relations. They are smaller algebras. Okay.
Yes.
I can give you a smallest.
I can give you a small example. Like you take the I think like the Laurent polynomials, like the analytic functions on the disk, that are analytic on the inside of the disk, but are just continuous on the boundary. And then because of the maximum modulus principle, so you can consider like either embedding this into the continuous functions over the whole disk.
Yes.
But because of the maximum modulus principle, it remains an embedding if you just consider it like evaluating it at the boundary of the disk. So you can also have the quotient like from C of the whole disk to like the continuous functions from the whole disk down to the continuous functions on the torus, just on the boundary of the disk. And in this case, even it is like this, that this one edge is like the maximal and the other one is exactly the envelope.
Yeah, thank you very much. Let's go on.
Okay, so having said that, we have this notion of hyperperiodicity. So it would be nice to know if our algebra is, if our operator system is embedded in a hyperrigid way in our C-star algebra. And to do that, we need the following lemma. So,
sorry, can I ask a question about this theorem and remark?
Okay.
So why this result above is called theorem when it is an obvious consequence of this remark?
Okay, so it is some kind of historical reason because we were able to prove this as a theorem without knowing that fact, and later on I just found that it was known as a more concrete theorem which follows from some theory of banda representation and so on. It requires more sophisticated machinery. But in that case, it was, let's say, the theorem in our first version of the paper, and we were able to prove it without any more sophisticated machinery than just using some basic facts we know about the operator system and the universal system algebra CMPO. So,
but how does the theorem follow from a remark? I see how remark follows from the theorem, but how do you have the equality into A? Or
no. In the opposite direction.
No, the other way around.
Yes.
Yeah, so the remark is more general.
Remark is more general.
Yes, the remark is more general. Yes.
Yes, yeah, of course. I mean, this is the remark that this theorem maybe okay. I should say that the remark is that this theorem was proven before in a more, let's say, general framework. Yeah.
Okay.
This is like okay. So this is the theorem we need, but the remark is that this is known in a more general context. Okay, maybe that's the proper way of saying that. But we didn't know about this, the other theorem where we were proving that. So this is maybe the way I am just presenting this, that using some, let's say, very elementary things, we are able to prove that under this assumption. But later on, we realized that this is not necessary, this assumption is not necessary. But at some point, we're really fighting to show that this holds. I mean, we know that. This is one of the ingredient we had. Yeah. So,
yeah, I really apologize for being confused, but just by knowing that the C star n of S is equal to C star of S, it does not follow that n of these two is equal to A, right?
yeah, I said that this should be equal to A.
Ah, okay. So
yeah, of course, because it doesn't make any sense to. Yeah. Okay, so we have this. So okay, so what is enough? It's enough to show that our operator system is hyperrigid in the C-star algebra CMPO, and this follows from the following, let's say, theorem or proposition that if I have two unital C-star algebras and C is another C-star algebra, phi is some morphism between A and the tensor product C and B, and S is defined as in our case, then if B is generated by S, then S is hyperrigid in B. And as a result, having this the first theorem on this slide, we have that B is a C-star envelope of S. And now we can apply this to our case because we know that all the assumptions are satisfied also in our case. So we know that C-star envelope of this operator system is CMPO for every finite P and compact O. Okay. And then this operator system has also the other nice property. So we call this property a strong extension property. We didn't find this property. I mean, there are a lot of different extension properties, but as far as we know, this one was not discussed. So we just call it strong extension property. But if it is known, I will be grateful for any comments about that. So we say that the embedding has a strong extension property if for every C-star algebra B and the UCP map from S to B, there exists a UCP map from A to B such that it agree with psi on the operator system S. Okay, so the thing is that we are using twice UCP here, and we don't assume anything else. So that's the reason to have this word strong here. Okay, and as I said, our operator system or maybe I should say our embedding has this strong extension property. Okay, so how much time do I have now?
2 minutes.
Okay, so I will skip the next part. It's just a reminder about the different notion of tensor products of operator system. So let me just go to the fact which follows from, let's say, the definition of the commuting tensor product. So there are different notions of tensor products of operator systems or C-star algebra or C-star algebras. And one of them is the commuting tensor product. And it turns out that for any operator system, there is a canonical UCP map from the tensor product of SPO tensor S into CMPO tensor S with the commuting tensor products. And as a result, and using some nice properties of those maps, we can show that the commuting tensor product of CMPO with any operator system is the maximal one. And moreover, there exists a UCP map from SPO tensor commuting S into this. I mean, this is just simple corollary of those two facts. And moreover, if we have a finite quantum space E and a compact O with CO separable, then for any operator system, this map is a complete order embedding. And just using this fact twice and some other properties like the symmetry of some functor and so on, we can show that this map is a complete order embedding. Okay. And having said that, we are able to discuss the other property of the C-star algebra CMPO and its associated operator system SPO, mainly the lifting property. So the lifting property is that if I have a CCP map from A to the quotient, then it can be lifted to the algebra B itself. And in the unitar case, we can replace CCP by UCP. CCP means constructive, completely positive. And it is known that the algebra from the work by Brown has this property. And the question is, of course, what in our case? So the first attempt to check if this is true is to look maybe at the well-known example, well-known cases like the nuclear C-star algebras, which have the lifting property by the theorem by Choi and Effer, so it's like 76. Yes. And this is nice, but the problem is that our C-star algebra is almost never nuclear, so we cannot use that. And okay, I just make some summary why it is not nuclear in, let's say, generic cases. So there are some arguments, but the basic idea is that this algebra subjects onto the non-nuclear one, and we can then deduce that it cannot be nuclear in those cases. So there are some kind of generic, not all cases, but let's say almost all nice cases. In almost all nice cases, this algebra is not nuclear, so we cannot use this as an argument. So maybe it's not true. This is true, and turns out that it can be proven that if we have a finite quantum space and O such that CO itself has a lifting property, then the algebra CMPO has a lifting property. And the same is true for the operator system. And we observe that this is similar to the case of RDF. The RDF was also about the RDF of CO. And in this case, this is about the lifting property for CO. And this is in some sense generic for the behavior of this algebra CMPO. Okay, so now let me go to the last part of my talk about dedicated to the quantum correlations. I will try to just summarize the main results without going into too many details. So for this thing, I need both spaces to be finite. And we define the so-called positive operator valued measure in this context as a UCP map from CO into BH. And we define the quantum family of PO VMs as a UCP map from CO into CP tensor BH. And for that family, okay, this is the, let's say, basic object. And the quantum correlation for us is any UCP map between the tensor product of CO and CO and the tensor product of CP and CP. We say that the correlation is non-signaling if this property holds. So in other way, you can say that if you have this interpretation in terms of games, the players do not communicate. So this is some kind of a formulation of this idea in this framework. And now we would like to characterize some kind of correlations. So we would like to first characterize so-called realizable correlations. And why realizable? Because they can be realized using some different objects. In our case, they can be realized by two maps, phi1 and phi2, and a state omega on BH. So if T can be written in this form, then we say that this is a realizable correlation, and we are assuming that the maps phi1 and phi2 are such that they commute on the second leg. Okay, so this relation is satisfied. And one can easily check that for any such two maps and any omega, this maps is a non-signaling correlation. And this is something which is, let's say, the first, in our case, was the first, let's say, first motivating observation to have some kind of characterization of such kind of correlation. So we can characterize such correlations in the following way. So we can say that it can be written as in the previous slide, or we can do the same, but now instead of those UCP maps, we can use a unitary star homomorphism and just use the, let's say, sister algebraic version of the previous description. And also it turns out that those correlations can be realized as a states on the maximal tensor product of CMPOs or the commutative tensor products of the operators of the operator system. Okay, so the last notion I would like to discuss, and this will be, okay, this has to be very brief because I'm running out of time. So this is the notion of synchronicity. So we have a finite quantum spaces, so we take some concrete decomposition. So all the notation here, all the notations are just standard ones. So we have some basis of the C to some powers. We have the units in matrix algebra as just the standard decompositions. And we consider the coefficients of those maps with respect to those bases, okay? And then we define the synchronicity as the following, by the following equation. So we say that the correlation is synchronous if this strange equality holds. And it may be quite surprising why, but let's see on the classical case. So take M and N equal 1, no internal indices, then we can identify those numbers with the probabilities. Okay, and we know that this condition, okay, this is 1 in our case, and this condition then means that whenever K is different than K prime, then this thing is 0. So synchronicity in the classical case means that if we ask the same question to two players, then they should give us the same answer. So this is written in a different way. So this is like the generalization of the classical synchronicity. And as in the classical case, we know that we can prove that the synchronous correlations can be described in terms of some maximally entangled state. And this is true in this case. So T is synchronous even only if the following equality holds. So this phi is this maximally entangled space. So this is the analogous property. And okay, again, we can now look at the realization terms of the states on the tensor product and then ask about the properties of this. So we can, for example, show that if we have a, okay, we know that since this is an LDF, there is a trace. So we can find now state phi such that this equality holds. And then we can put this state, just construct this this correlation T, and then this T will be synchronous. And the last slide of my talk is the description of this of those correlations in terms of tertiary states. So this is the, let's say, the summary of what is meant by the fact that synchronous realizable correlations arise from tertiary states on sister algebra generated by operator associated to the maps in the realization of this on this state. So actually, you just have those operators into the compositions, and then you can check what happened with the state on the restriction to the C-star algebra generated by those operators, and then it can be shown that there is a trace. So this is the one of the properties. So this, let's say, the way of saying that the correlations of those types arise as a tertiary states. So this is like the generalization of what is known in a classical setting. So in some sense, this strange definition of synchronicity makes sense because we can reconstruct most of the properties. Okay. So that's
can you remind me what this NP stands for?
NP is the number which appear in the decomposition of.
Ah, okay. Yes, sorry.
So
yes, this is
the number,
the number of components defining this
yes.
job. Yes. Okay. Thanks.
Right. Yeah, and this is quite interesting that we don't have an analogous version with NO. There is some notion of bisynchronicity for other, let's say, applications, but it is not just straightforward replacing NP by NO. So this is, let's say, some other comment. This is not the same. Okay. So having said that, let me just go to the conclusion. So we just studied we studied the quantum space of maps between quantum spaces. And we were able to show that the sister algebra associated to this quantum space has the Rifty property, is RDF. And in some sense, the embedding of the corresponding operator system in the sister algebra mimic more or less all the properties we know from the classical setting. So this is like the good candidate for, let's say, quantum analog of quantum correlations. Okay, so that will be all for today. Thank you.
Okay, thank you very much. Any further questions?
I have a question.
Go ahead, Tom.
If you have mapping spaces, then you have the evaluation map. And this evaluation map is, in your case, star homomorphism. But at some moment, you are replacing the algebra of functions on this mapping space by the operator system. Assume that we have classical finite sets. Okay.
Mm-hmm.
Can this operator system be described in classical terms? In terms of these finite sets, what is this in terms of these finite sets?
Maybe you should go back to the slide with this SPO.
Yeah, yes. I think this Q, where is this? Definition is here, but the classical case you can take C equal 1, right?
Yes. No, I would say N equal 1.
Sorry, N equal, of course, yes. There will be no matrix structure, of course.
Yeah, that's what I suggested for an example. So when you said it's trivial, it wasn't so trivial. Then you would have exactly the commutative sister algebra of functions on C points. You know, it makes sense.
Yeah, right, of course.
Yeah.
Okay, so you take N equal 1 and.
So then this will be.
So QAs simply.
Yes, so just now, right? I mean, okay, right.
And
now structure.
What are they in terms of these finite sets? or maybe it doesn't have any set theoretical interpretation.
Well, they should have. Just remember now. Maybe go to this. That doesn't help much.
Yeah, so you see in this lemma, you have the map from C of O to C of P tensor CPO.
Yes.
So if you replace this SPO by the sister algebra of functions on
But wait, SPO is not a sister algebra, is it?
No, it's an operator system.
Operator system.
But
An
you said
operator
sister
system.
algebra.
No, it's an operator system.
Yeah, but you said sister algebra, which is wrong.
No. C of O, if you replace this operator system by the sister algebra generated by this operator system, you obtain something which is dual to the evaluation map.
So you want to replace SPO by what? The sister algebra that generates?
Yes. So CPO generates MPO.
Yes.
C of MPO. So
Yes.
this makes perfect classical sense. It's an evaluation map, dually written. Okay. So I wonder what is this UCP map in terms of classical notions of maps between finite spaces, finite sets even.
Yeah.
Does it have some interpretation or not? It's an exotic construction making sense only in non-commutative.
I think it should be possible to express using the thing we had for P operators. Right? We had this description for the P operators. So in this case, okay, I'm trying to.
Yes, but this time you have a PMC, which is a sister algebra.
Right, yes, exactly.
So in fact, this alternative point of view, it is a special case what I wrote in red using this annotate function. Okay, when this algebra B is simply B of H. Okay. So this is not the answer to my question, because you have already this P and C being a sister algebra. It's not an operator system. So I was asking rather about this lemma you showed a few seconds ago. Does this lemma have some set theoretical interpretation for finite sets? Yes, this one.
I don't have the answer right now. I can think of it.
So my question is a little bit related to the question of Paul Baum at the beginning.
Okay.
Yeah, how you generate examples and what it is we are talking about. Yeah. Okay. Anybody else?
Well, maybe about those examples we started to think, but we didn't finish this. It was about the games between quantum graphs that was one of the possible examples of realizing this in practice, but we did it, so we don't know if this is the example or not.
Okay.
That was the natural generalization of something which was done in the classical case, but we don't know, so that's the answer. We didn't do that.
So since there are no other questions.
I have another question.
Sorry. Oh yeah, go ahead, Jacek.
Yeah, so I would like to go back to the question that I've asked before. So I understand that. So you have a theorem that asserts existence of the sister algebra function on quantum space MPO in the case where P is finite and O is compact. So I understand that you cannot generalize, you cannot hope for a generalization too much, but for example, do you think it would be possible to generalize this situation to the case where O is still compact but P is discrete, but possibly infinite?
There is some, okay, so instead of having P finite, we can in some, okay, I think that we were able to show that P is some limit of some type. I don't remember now the details because we didn't finish this argument in full glory, but it can be slightly generalized, but not so much. So it's like something like direct, or okay, I don't remember which kind of limit it is, some kind of limit of finite spaces, but not too general. So I'm not sure what is the most general formulation of that, but okay, most of the properties you wanted are not satisfied if we are going beyond P finite. So in too many places we need to have finiteness of P.
Okay,
so
and what about
even classically? Imagine that you have for P take the set of natural numbers, and for Q take unit interval. So you end up with the space of all continuous maps from natural numbers to the unit interval. So this is the same as the space of all possible sequences with values in 0, 1. And the natural topology on the space of all continuous maps is the compact open topology, which in case of a discrete space boils down to the pointwise topology. And you end up with the Hilbert cube, 0, 1 to the natural number. And this space is
compact.
Yeah, exactly, which is compact.
Yeah, that's why I mentioned the discrete.
Yeah, this was when I
see.
understood that's motivation. That's exactly the motivation. Yes.
Indeed. Okay.
Might be no longer metrizable, and it's more fancy topological space, but
It is metrizable.
oh, it is okay.
For accountable.
Yeah, for accountable. Yeah, for accountable. Yes.
Okay, but I understand that in the proofs, the finiteness assumption is kind of useful. So another direction to generalization would be that you keep P finite, but you make O locally compact. How about this case?
This is a very good
That's
question.
a good question. Right. Okay, so maybe let me just mention how the proofs
This
are
should
going.
work.
Possibly.
But isn't it so that if P is finite, then automatically O has to be compact?
No, why?
No.
Why?
No.
Classically, you still would have finite product of locally compact spaces, I think.
Exactly. Yeah.
Okay. Yes, you are right.
So the way to, so there are two proofs here. One of them is that say old technical proofs, which is based on the previous one that was done under the assumption that CO is finitely generated. And then you can drop this assumption by just consider some full group C-star algebra and make some, just you can mimic the finitely generated case in the let's say full glory without this assumption. And the other proof can be deduced from the fact that we can describe the space in terms of free product, right? So the description in terms of free product allows us to prove this in some more general setting than just fine generated. So that was the way we proceed. And I am not sure if you can go much further with that. We didn't find the way to go further, so that would be the answer.
Okay, thank you.
I don't know if there's any.
All right, so there are no further questions. Let me scroll through all the all the people in the audience. No, I don't see any raised hands. So Arkadiusz, what is your take-home message? What is the main result? What it is that you would like us to remember from your talk?
Okay, that's a good question. Maybe that the hyper rigidity is important. I don't know. That's one thing. Yeah,
yeah, but I mean your result. I mean, which of your results, of your contribution to science, is the key one in your presentation?
I mean, from, yeah, I mean, in some, okay. That's a good question, tricky question.
So what is the main obstacle that you managed to overcome that it was not overcome before?
Yeah, okay, so in some sense, the main one was to use the Kasparov theorem here, because in the most of the previous proofs with about similar things for different sister algebras, the techniques were based on ones introduced by choice, so some multiplicative domains and so on. But here the novelty is in some sense to make an extensive use of Kasparov theorem, so to somehow see that this is the main thing. So the separability of the CO space is really important. That's the crucial thing too, because all the other versions can be other theorems, previous theorems. Not all, okay, most of them can be somehow proven using Kasparov using Kasparov in different places. So you can really replace some of the huge technical proofs by this, let's say, important results. So this is like the observation that here the Kasparov is important.
But which result is this? Can you show the slide with this?
For example, you had this, where is the lifting up? Where is this? Okay, so no, where is this? So I have to find the. So most of the results where we are using the separability are because of the fact we are using Kasparov. So it is not an accident that we are just assuming the separability here. It is because if we have the separability of the sister algebra corresponding to the quantum space O, then the Kasparov allows us to do a lot. So it's like it's not like a single lemma or single fact. It's just some kind of generic thing here that the separability is crucial. And the other
this is novelty in technology. What is a result that you would like to pinpoint as your highlight cherry on the cake? And there's no single result here, because this is like set of results rather than a single one. So it's like so point to the first one.
So the first one is this lifting property for this CMPO. The other one is IFD of CMPO.
Yeah, okay.
Yes, okay, IFD of CMPO, because having IFD, we're having cases, so we are having the descriptions of correlations in a nice way and so on. So let's say the starting point, the most important fact is that CMPO is IFD. This is the important thing here. Right? Because if you have a IFD, then we have traces, and that's like the first step to have the description of correlation type of traces, because everything is usually described in terms of traces or some space and so on. This is like, we need something to have a trace, and this something is RDF.
You need something to have what?
To have traces.
Traces?
Yes. So the simplest way to get it is to have the RDF property. The simplest, one of the possible ways to have this RDF property. And in the theory of quantum information, this is used many times.
Okay.
Different contexts, of course. But so this is like one one thing which is important here, that this RDF is here.
Okay, so I think it's a good time to stop.
Sorry. Could I ask a question about these two theorems? Are these theorems independent of one is a consequence of the other?
Okay, that's a very good question. We were thinking about that, but I'm not sure that this is like a conclusive answer now. I mean, the techniques are quite different. I mean, it's possible that one theorem plus some other assumption give us the other one, but I'm not sure that this is direct consequence. We didn't prove it in this way, and we were looking at that, and I think that the conclusion was that there is no relation between them in general. But in some cases, I don't remember now the assumption, but most of the assumptions are always about the tensor products of those operator systems. Right? You had this the whole story about the, I think it was called Cashback Conjecture, right? And there was some story about this different kind of lifting properties. And all of this, I mean, this is very similar in some sense. I mean, the properties of those, what is this? Those embeddings, that those operator systems sits in a proper tensor product and so on. So everything is related to that. In some sense, there's some connection to this kind of constructions. I mean, it's not like one-to-one correspondence, but they are right. So in some sense, we can expect some implications between, I don't know, some kind of extension property, lifting property, and so on, but we didn't explore this in detail, so I cannot answer this right now.
Okay. Thank you very much.
Okay, so let's thank ARKADIUSZ again. Thank you so much. And I stop recording.